My name is Jacob Farley, and this is Lab 4 for Physics 2 bar magnets. The purpose was to measure the distance dependence of the magnetic field due to a smaller bar magnet and to compare the measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart laws. The experimental model was the bar magnet in the lab, and the computational model was through GlowScript. The overview was the magnetic field decreases the further from the magnet, and the parallel axis experiences a twice as strong magnetic field than points on the perpendicular axis from the same distance. Our n value was negative 1.2657, our k value was 8.073 times 10 to the negative 6, and our mu value was 4.773. The fundamental principles are the magnetic field versus distance, the equation for the on-axis B field, and the Biot-Savart laws. Our initial conditions was the system, which was the phone and the magnetometer, and the surroundings, which was just the bar magnet and Earth. The design was we determined a location of magnetometer chip in the cell phone. We kept the magnet in the same place, and then we found distances at which the B sub x values are equal to 20 mu t, 70 mu t, 120 mu t, 170 mu t, and 220 mu t. And then we found a distance where B net was equal to 100 mu t, and we recorded it. And then we determined the x, y, and z components of the net magnetic field at that distance. Then you correct the y component and calculate B net, and then repeat 3 times an average. This was our results, where you can see all of the values that we found experimentally, and then we even graphed them and put them through a table. We got the equation that y equals negative 1.2657 x minus 11.727, where the y-intercept is equal to the natural log of k, which is 8.073 times 10 to the negative 6th, and b bar is kr to the power of n, which is mu naught over 4 pi times 2 mu divided by r cubed. We observed that when magnetometer gets closer to the bar magnet, x component of the magnetic field increases, and that the x component of the magnetic field will be close to 0 when it is very far away. This was the code for my computational model. It's a little blurry, I apologize for that, but it details all of the code necessary in order to model this. And it gave us an off-axis B field of 9.529 e to the negative 6th, 2.859 e to the negative 5, and 0 in the z component, where the specific results and diagram are shown on the right, which is different from our observed, which was negative 1.173 e to the negative 5th, 1.63 e to the negative 5th, and then a real z component, which was negative 2.527 e to the negative 5th. So our error in observation could have come from measurement inconsistencies, movement of, like while measuring, and nearby electronics interfering with the magnetic field. Finally, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The x component of the magnetic field would change, which would change the values of n and k and create a greater difference between the experimental and computational results. If we were to stick 2 identical magnets together end to end and run the experiment again, how would we expect our measurements to differ? The magnitude would double with no change in direction of the magnetic field superposition. Thank you.